All right, can you all hear me okay? Good. I know voice production is cool. I'm here to convince you that perception and the brain are cool as well. So I'm going to just start off with some of my premise here, some of the themes of organization. One is that for us to understand speech, we have to deal with a lot of variability. For us to understand voices, we have to deal with a lot of variability. And we are hit with about 16,000 spoken words daily. In this talk, you're going to hear about 1,000 words from me, all right, and maybe many thousand phonemes, and your brain has to do this construction. And if there's a phone near you, or if you're on a laptop, you're probably going to hear 1/3 of that. So voice and speech is inherently variable, and it often occurs in a lot of background noise. At the city center, that's about 68 dBA in the afternoon, and you have to deal with it coming rapidly. So 4 to 12 syllables a second. That's incredibly fast. And when we are trying to understand a speaker, you're also keeping track of a lot of other things. The identity of the speaker, is the speaker familiar, unfamiliar, what the age is, what the sex, the emotion, dialect, size, and prosody. And humans are incredibly good at this, so they're not very far away from telling somebody's age, what the size is, just based on their voice. I'm going to give you an example here, which is pretty dramatic. This is the Hindenburg disaster. I'm going to play the video.
At times the rain had slacked up a little bit. They attached the motor to the ship, but just holding it just enough to keep it from... The person in the front, get it started. It's fighting and it's crashing. It's crashing terrible. Oh my, get out of the way, please. It's going to be bursting into flames and it's falling on the morning fast road.
So this was an explosion that happened in 1937, and it was probably the first live coverage of an event. And Herb Morrison, who was representing the Chicago radio, was there. He was not planning to cover a disaster, but it just happened. And the first segment, he starts off just a normal address, excited, and is communicating a lot of information. And then once the explosion happens, his voice changes completely, as does his intonation, his emotion. We're keeping track of all this, but the question I like to ask audience in general is, can you guess this person's age? And they're very, very accurate. Approximately 40 years of age. And they can even guess the dialect, they can guess a lot of things despite this tremendous variability. I lost my bags through American Airlines yesterday, so I dealt a lot. This is from Banana Republic today. But I had to deal with a lot of customer service, and most of them were bots. And for some reason, people look down at the field of speech and language processing saying, oh, computers have solved it. They really haven't. I can tell you from my experience. I can give you an example. So what I've done here with the help of my postdoc, Zheshen Guo, is use OpenAI's model. So the speech audio from what you heard before was transcribed by OpenAI. And then we used a very popular model, the Wave2Vec 2.0 through Meta, to train on many different features. And I'm just going to orient you really quick. We're going to look at the fundamental frequency changes as Morrison is talking. And please notice that immediately after the explosion, it's going to fluctuate a lot. And it's going to come at you at the rate of speech. So that's what the dial is going to tell you, is how fast somebody's speaking. And then the model is pre-trained on female talkers, male talkers, children. So it's going to try to predict based on the audio, who the talker is, and what the age is, and then what the valence and arousal metrics are. These models are out there, and so we've just used one of the pre-trained models.
It's starting to rain again. The rain has flagged up a little bit. They passed the notice of the ship are just holding this just enough to keep it from... It's worse than the flash. Get it started. Get it started. It's fire and it's raining. It's raining terrible. Oh my God, boy, please. It's running, bursting in the planes and it's falling on the flying fast and all the folks to believe that this is terrible. This is the worst catastrophe.
Just going to pause at a random moment, right? So this is the first time when he's getting really agitated, and the model, which was doing just okay, suddenly just starts falling apart. It's misrecognizing the gender, the age is way off, and the arousal metrics are off the charts. But you can also see that even though I kind of oriented you towards the voice, there's a lot of information being provided by this individual. And OpenAI is able to do a pretty good job in transcription, but again, it falls apart once all these other features are added. This is a hard task, currently not solved by AI, and it's getting there. How does our brain solve this issue? Okay, I'm gonna argue through the entire talk that we use a lot of top-down guidance in Percept. And there's much more to voices, to spoken language than meets the ear. And I'm going to derive this idea from a model that's very popular in vision, but is not quite made it big in audition. And it's the reverse hierarchy theory. The reverse hierarchy theory argues that whenever you're dealing with perception, you're always trying to solve it at the highest level possible. The gist, the object. And if you're not able to solve the perceptual task, then you go lower and lower in the hierarchy until you're able to use very, very fundamental cues to solve the perceptual problem, right? So perception is right at the top. And learners, if people are trying to learn a new voice or learn new speech, this is what they do is try to get the gist, get kind of a category representation going, and use that to kind of fine-tune sensory encoding. And so this is a model that we'll be testing throughout the many studies I'm going to show you. But just to kind of wake you up, I'm going to do a couple of audio examples, or 3 examples. One is verbal transformation. Okay, so you got to watch the video. I can assure you it was only Bill played again and again. So that is verbal transformation, nothing new. This was, Warren in the 1960s showed this happens. And it's basically your semantic system getting really bored. We rarely encounter repetitive sounds, so it's just making things up. And one more dramatic example is sine wave speech. So speech that only has the first 3 formants, every other structure is removed. And when you play it, it sounds like this. Okay, can you understand anything there? If you did, you're going to spoil this. All right, this is the original speech.
The man's painting a sun.
Do you feel that pop out? Right, it was almost recognizable. In fact, people can recognize talkers just based on those pop-outs, even though we traditionally think of the cues of fundamental frequency and harmonic structure being so important. But you can recognize who a speaker is just with sine wave speech once you're oriented towards it. All right, another phenomena or illusion that my lab's been working on quite a bit, it's kind of interesting. How many of you have heard of the Laurel-Yanny stimuli? I see a few hands here, so it's new to a lot of people. So this is the audio equivalent of the gold dress, blue dress. And for literally 2 days, speech scientists and neuroscientists were really, auditory neuroscientists were really popular in the media, and then went away, right? Okay, so for those of you who have not heard this, this is a word that was generated, it's synthesized speech that a teenager posted to Twitter, and basically found that different people had different percepts. And this is what it sounds like.
Yeah. Yeah.
All right, quick show of hands. How many heard Laurel? How many heard Yanni? All right, just look around, right? That's 50-50. And those of you who heard Laurel, were you fairly confident that you heard Laurel? Yeah. So this is remarkable, right? The same audio, which is ambiguous because it's synthesized, it doesn't have the cues that you have in natural speech, but completely different percepts. And if feel free to go ahead and point your camera there and take the survey. I'm not going to use any of this data, but I'm very curious. Right, so that is where percept is right now. 56% say Laurel, 28% say Yanni. Now, we've been interested in revisiting this phenomenon. It happened in 2018, and since then we had a global pandemic. There's been a lot of changes to audio codecs. There's been changes to how people listen to audio through loudspeakers and through headphones. And it turns out people are now shifting their bias slightly from Yanni to more Laurel. So if you're older, if you're male, if you're a musician, and if you listen through headphones rather than speaker systems, you're more likely to hear Laurel than Yanni. But it still doesn't explain how this audience here is 50-50. That is not my experience. It's usually a lot of Laurel and very few Yanni. Right, so that sets the stage out here, right? So I'm gonna spend the rest of the fun part's gone, by the way. Now we'll go to science. We're going to talk a lot about various studies here, and this is what my lab does. We don't think about speech, we don't think about voice, we think about how the brain categorizes information, right? And there's much to learn from that approach, where you're asking the question, how do people solve variability and do this many-to-one mapping from incoming sensory stimuli that is ephemeral, really fleeting, and how do they extract that and transform it into discrete categories? And those three examples I gave you make the case for the talk, which is that we are very stable despite all the variability. So we're going to look in the brain about how our representations emerge for new categories and how robust they are to variance. We're going to talk about how our sensory systems are shaped by top-down information on a constant basis. I'm going to spend a little bit of time talking about individual differences. And I feel like that might be a connecting point between some of the work that you do and some of the work that I do, is the focus on individual differences and why people are so different in their performances. All right, for much of this talk, I'm going to focus on pitch, voice pitch, but use tone language as this very unique window into examining experience-dependent plasticity to pitch. Now, more than 50% of the world's population speaks a tone language, and I'm using example from Mandarin. So Mandarin has 4 tones, and the tones sound like this. Ma, ma, ah, ma. So a level tone, rising tone, a dipping tone, and a falling tone. So these tones can convey word information. So English also uses pitch contrastively, but it's not to the extent that Mandarin does. So it offers a really kind of nice comparison point when we compare native Mandarin listeners with native English listeners in how they categorize these tones, how they learn these tone categories. So that's part of what I'm going to be talking about. But just to set that up, tones are very easily acquired in early childhood, and there's really large individual differences. So people, if you heard it and you're like, oh, that's trivial, the challenge comes when you have to get the context out of it and deal with a lot of variability between talkers. And so there's large individual differences in real world adult acquisition of tones and usage. And so how do adults then successfully acquire these tone categories? So for that, we leverage a lot of prior work done by David Pizzoni and colleagues who looked at laboratory training approaches to get significant and generalizable learning. Now, this was thought to be an impossible task, learning difficult non-native contrasts as an adult. But we do know that even difficult contrasts like the Japanese L's and R's can be acquired with perceptual and category training. Okay, and there are three kind of characteristics that adults seem to need. One is high variability training, so lots of exemplars, lots of variability, lots of different talkers, a lot of different contexts. Throw in variability, that's good. Trial by trial corrective feedback. So unlike infants that are having unsupervised ways to acquire these categories, adults seem to need feedback, right? So you really need to attend and use feedback to correct your errors and learn. And thirdly, there's a lot of work in using synthesized speech, and the field's now kind of moved towards natural speech. And that seems to really help when there's a rich redundancy of cues. That is really helpful when you're trying to learn, right? So this is kind of the formula. This is well known since the 80s that you can get people to learn even difficult contrasts if you use these three kind of approaches. What is less known is how the brain kind of works in the process of learning. And that's what I'm going to kind of show you, which is how does the brain develop new representational categories for tones. So these are native English speakers acquiring tones, using pitch contrastively, and where are representations emerging, how resistant are they to variability. And the paradigm uses multiple talkers, both female talkers, male talkers, and what you will see are narrowband spectrograms here, so you can see lots of variation in pitch. But despite this variability, the participants, the learners are asked to categorize into one of four categories, right? So this is what it sounds like if you're participating in one of my experiments. Four different speakers, and you can see relative to the examples from Ma, this is a little harder, right? So now that you have to deal with multiple speakers. The paradigm we've used a lot, both in human models as well as animal models, is the sound to training category paradigm. So the participants hears a tone, it could be E, and they're asked which category is it, one of four categories. So that was tone 2. So if you hit 2, then you're going to get feedback, which is correct in this case. We've used this as our kind of benchmark paradigm, and we've done a lot of work changing subtle things about the paradigm, and we've also done a lot of imaging work where we can look at what's happening in the brain. But behavioral performance here we can get people trained up to some extent within a session. That's about 300, 400 trials. And so chance here is 25%. So 25% you're basically at chance. You don't know which tone it is. We get plenty of such people who cannot differentiate it at all. But for the most part, you can see the average curve looks like this. You have starting close to chance in the first block, and then over a course of 300 trials where they're getting feedback and multiple talkers, they're able to get the categories to some extent. Some do really well. Okay. What's happening in the brain? First step was to look at representations in native listeners. So these are Mandarin listeners in China who basically were asked to either passively hear tones or hear a tone and then try to covertly produce the tone. Or thirdly, hear a tone and press a button and make a category decision. Okay, so we argued that if there were true representations of these tone categories in the brain, then it should be independent of these tasks. So it should be task invariant. And it should also be talker invariant, because independent of talkers, you should have stable representations. And it's also resistant to the actual syllables. So that's what you're going to see are 3 brain regions where information from the brain, so these are voxel patterns measured using functional magnetic resonance imaging, voxel patterns that's thrown into a machine learning algorithm, and the machine tries to predict just with the brain data which category somebody's listening to, right? So 3 brain regions pop up, the left and right auditory cortex, the left superior temporal gyrus and the right superior temporal gyrus, and the left inferior parietal lobule. So these three brain regions have robust representations of tone categories, irrespective of variability in talker, variability in the task, right? So there are three regions. Now, these regions represent different types of information. So we used an approach called representational similarity analysis. So what it does is kind of tells you what is the underlying acoustic structure that drives the brain activity in these different regions, right? And it turns out that the right superior temporal gyrus is very sensitive to pitch height, so high versus low, which is a good cue, but not a great cue if you are looking for talker independent cues, because that's very talker dependent. The left superior temporal gyrus, on the other hand, had rich multidimensional structure where there was integration of both pitch height as well as pitch direction, and so it was much more robust representation in the left superior temporal gyrus. Now, what about learners? So, what about people who don't know Mandarin tones, and we're getting them to be in the scanner and learn these tone categories? So this is work from Hangyo Lee, his PhD dissertation, and he came up with this really clever design where he separated out the stimulus and response from the feedback window, so we can measure the brain responses and the brain representations of the stimulus independent of feedback. So remember, people are also getting whether it's correct or incorrect. And so what we wanted to do was study the whole brain in action. So all the work till then had looked at pre versus post contrast, but what we were trying to do was in the process of learning what happens. Okay. What happens is early in training, so the first half of training, there's already robust representations of syllables, so that's in blue. So these are native syllables, so that makes a lot of sense. So this is information in the brain that can be decoded to figure out which syllable there is. And that's in the left superior temporal gyrus. In the second half of training, what we found, which was really surprising to us, so this is within a few hundred trials, we're seeing a representation emerge in the left STG for the learners. Right? And this representation also seems to be very robust, multidimensional, very integrative of cues related to pitch height and pitch direction. And so that was really exciting. We followed up with this work looking with collaborators at UCSF to look at patients with intracranial recordings. So this is electrocorticography or ECOG. And this can give us, so fMRI gives you a good sense of the larger structures involved and how they talk to each other, how they're connected. But intracranial recordings give you granularity and timing precision. And so we followed up this work with patients with electrodes that are inside their brain for clinical purposes. So they're participating, volunteering to be in research. And what we find is that the electrodes, so electrodes here are really tiny, so they capture maybe 100 neurons. These electrodes change as a function of learning within that session. But what's really happening is it's not all electrodes, it's only electrodes that already have high variability. So these are electrodes or neuronal ensembles that were inherently more variable that showed the effects of learning. And that makes sense. Now, what happens to performance feedback? So when people get correct or incorrect, it's a simple design, right? So all they're seeing on the screen is correct or incorrect. No complexity to it. But what we see is the whole brain light up when it's correct relative to incorrect. And the parts of the brain that light up or active involve what we call as reflective processing regions. So these are regions that use feedback to develop rules, analyze rules, and then change the rules if necessary. So if you're getting negative feedback, then the rules get optimized and adapted. We also found a lot of brain regions that capture reward value. So these are the dorsal and ventral striatum, Incidentally, these regions are not specific to tones. They're activated by voices, they're activated by music, and it reflects reward-based processing. And then we also found the anterior cingulate, which is involved in error monitoring and guiding behavior responses. So when correct pops up, these participants are really excited. Some of them are really analyzing and overthinking this. And then some of them are using that error constructively on the next trial to get things going and do better, okay, which brings you more reward. Now, we looked at functional coupling, so how are brain regions talking to each other? So remember the left STG, the superior temporal gyrus, is where the representations emerged within the second half of training, and then the putamen, which is active for correct versus incorrect responses. So we are looking at now across learning, the time course of learning, what's happening, right? How are they connected to each other? And it turns out early in training they don't talk to each other, but second half of training, when these representations are emergent, when you get a correct response, incorrect response, the striatum really seems to get more connected to the superior temporal gyrus. Now, we cannot discern directionality with this approach, but our prediction is that when you get an incorrect response, the striatum, which really wants that reward, it's really excited by the reward, is fine-tuning the representation at the superior temporal gyrus, so that that representation then drives your behavior and it gets a lot more reward. Okay. And what's really cool is that we had a measure of structural connectivity prior to then doing the experiment. So these are just the cables between the region. What is the integrity of the cables? So this is a technique called diffusion tensor imaging. And what we can show is that those with more integrity between these two regions with respect to anatomical connectivity were better learners, but they also showed more robust representations of categories. So even before you even start this task, I can give you a sense just by your brain data if you're going to be successful or not. All right, we're going to switch gears a little bit here and talk about sensory encoding. And so much of the work I talked to you about before was functional magnetic resonance imaging, which is great for capturing network level neuronal responses. But this approach here with electroencephalography is not great to give us an indication of where in the brain things are happening, but it's awesome to give you temporal precision. So when are things happening? And it's great for something like speech where temporal precision is super critical. So we need to capture information within a 20 millisecond window. So this approach is great because it does exactly that. And within the electroencephalography approach, we use something called the frequency following response. And 10 years ago, nobody knew about this, and I had to spend many slides getting people up to date. But now, you can see the graph here to the right. The reference to the frequency following responses have been really kind of rocketing up, and that's because they're really cool, right? And if you're interested in pitch, this is really great because what you can capture with these responses, which reflects phase lock activity from ensembles across the auditory pathways, is periodicity information, right? So if you have a periodic stimuli, so like speech or music, or people use cries, it gives you kind of a neurophonic where you can take the recording, which is measured from the scalp. You can measure it when people are asleep. They don't have to be particularly attentive. So much like the auditory brainstem response, we can pretty much use this on anybody. Lots of work on voice production and the frequency following responses. It gets suppressed in the brain when somebody's producing a voice. I don't know why I had to slip that in. I feel like I'm losing your attention. So the frequency following response, I can talk about this a lot. I think it's really cool, but I'm going to switch gears really quick. So what we can do is take the recording from the scalp, convert it into a wave file. All right, so remember the 4 Mandarin tones. So that's what I'm going to do. These are the 4 Mandarin tones. It's fast. And this is the first audio again, and then you're going to hear the brain response. noisy version of the stimulus, but you could hear the semblance of pitch being stable, rising, dipping, and falling, right? So this neurophonic has been used quite a bit to understand sensory encoding of periodic information. And some groundbreaking work in 2005 from Krishnan and colleagues at Purdue showed that native listeners of Mandarin, when they are listening to these Mandarin tones, their frequency following response, which conveys early encoding of periodic information, is much more precise than non-native listeners. So if you're a native Mandarin listener and you're listening to your tones of your language, your fidelity is really good. And we're not talking about fidelity at much post-processing. This is encoding fidelity, right? So this is predominantly from the brainstem. And a few years later, Wong and colleagues followed this up by showing that the encoding fidelity, and so what you're seeing here is the blue track is the stimulus pitch, and the yellow track superimposed is the pitch extracted from the brain response. And you can see that they are very related to each other. So the more related they are, the higher the stimulus to response correlation. That means there's greater fidelity. And what they did was take English listeners who never listened to Mandarin, or at least they self-reported they did not, and divided them into those who were musicians, so more than 10 years of musical experience, and those who never played a musical instrument. And what they found was the frequency following responses to these tones, even though tones are not relevant to the English-speaking musicians, was much more precisely encoded in the musicians relative to the non-musicians. Right? So this is really cool and groundbreaking. We followed this up by looking at both musicians and Mandarin listeners across multiple days. So the same experiment, but we had people come repeatedly, so 3 to 5 days. And we found that it was stable, so lots of exposure to these tones did not make the English listeners anything close to Mandarin. Right? So they were still less effective. So they were still tracking, but they're not as effectively tracking the pitch as the Mandarin listeners were. So we asked the question, can we change the frequency following responses with lots and lots of training? And the partial answer was a day of training was not enough. So we did some pilots and showed that that didn't change. And so what we then moved on to was a much more comprehensive training paradigm that became a part of a dissertation for Rachel Reedsky. And Rachel now studies the frequency following responses in autism spectrum disorders at Johns Hopkins. What she did was have 20 participants who were naive to Mandarin. This was before the days of prolific and virtual testing, so she literally had them come to the lab every day. They were very committed, and had them do the same task over and over again. Okay, and we had a very set idea. What we wanted to do was have people when they're novice, so measure their frequency following responses before training, and then train them up until they got to 90% accuracy, which is the same accuracy as native speakers, and for 3 consecutive days. And then we told them, you're not done, 10 more days of training, okay? And then we let them go and then ask them to come back after 2 months to do post-training frequency following response. Firstly, behavior was very surprising. So remember, lots of variability in the first session, which is kind of what I've shown you before. But we can train that variability away with over time. So people get really good at this task, and they take different trajectories to reach their performance targets, but they do. Okay. What's really cool is 8 weeks after training, when we bring them back, they're just as fast and as accurate as native listeners. So whatever we've changed that behavior. Now they're not going around speaking Mandarin, right? But they know Mandarin tones really well. We had 2 tasks. In addition to the frequency following responses, we had a measure of categorical perception. So we created a continuum from level pitch to rising pitch, and asked people to make a call, is it level or rising? And what we see in native listeners is a very classic categorical perception curve. So the sigmoidal curve you see, and in non-native listeners, so I picked a particularly bad one. Most of them had something going on. We can calculate the slope as a measure. So I'm comparing two measures here. So the categorical perception, which reflects more top-down, goal-oriented decision, and then the frequency following responses, which is much more bottom-up sensory information. And there were two kind of hypotheses we had. One was that this is based on neuroscience work from visual learning literature that suggests that early on there's changes to sensory information. That is kind of the initial stage of learning. So sensory information changes. So what you see is an autocorrelogram of tone 2. And so something's happened that engenders better learning. That's the signal enhancement theory. To contrast that, we had the reverse hierarchy model, which suggested that learning creates this type of top level, gist level representations, and that drives sensory encoding. Okay? And so learning happens, you get really good, and then the frequency following response change. And what we found was really interesting. So on the top, you see the categorical perception curve. So when they were you can see a big difference between native and novice. By the time they're experienced, so this is 90% accuracy, the non-native English listeners are getting more categorical, okay, in their behavior. And that's sustained through the different stages. And even in retention, they're more categorical. They're still not as categorical as native listeners, and that makes sense. We're talking about people who have tons and tons of experience listening to tones. What's happening to the frequency following responses? Well, you can see the big difference between native and novice frequency following responses, and that's just a replication of prior work. When they're experienced, it doesn't change, but then there's a dramatic change when they're overtrained. Okay, so when they come back after 10 days of training, suddenly their frequency following responses have changed, which means their sensory encoding has changed. What's really interesting is that plasticity is retained. So early brainstem structures encoding this information has changed as a functional experience, but it's also retained after 2 months of no training. Now, what I casually mentioned was that there's a lot of individual differences in learning. This is just 4 different studies in the lab where we had different participants come and do the Mandarin tone learning task, and you can see lots of variability. The last one is about 200 participants where we also had genetics data, and there's a relationship between genetics and individual differences. But we put all our data together, and we had 700 participants here. And you can see, again, these are non-native, as homogeneous as possible. So they're not musicians. These are mostly undergraduates at University of Pittsburgh and University of Texas. Nothing, that is dramatically different about any of them. But we can see lots of differences in learning. This led us to a model which we call the dual learning systems model that was devised to explain some of these individual differences. Now, remember I showed you a snapshot of the brain processing feedback, and there were parts of the brain that were very reflective, parts of the brain that were more reflexive. And so we then did a lot of neuroscience experiments to map out these pathways, the sound to rule systems. So here's where somebody hears a sound, and they develop a rule on the basis of it. So their encoding doesn't need to be fine-grained because it's a rule, so they map it quickly to a rule. But they can also use another pathway, the sound to reward mapping pathway, and map sounds to rewards. And so this uses the striatum predominantly, whereas the reflective system uses the prefrontal cortex. So if you're doing this task, you're hearing these stimuli, you're like, why am I making errors? You're being reflective. And when we ask to debrief, participants say something like this.
Words that are flat, meaningless, so you don't need to accentuate.
They're talking about the rules that they developed to solve this task, right? Very reflective. Another participant is also performing exactly the same level, 80% accuracy, and this is what they say.
I don't remember category 4.
They have no clue. Same accuracy. Okay, so this person is going with the gut, and what we are arguing is that that gut is not like just trivial, but it's sophisticated. That's your basal ganglia analyzing what it takes to get a reward and adjusting performance on that basis. So this model, we argued, is that something like speech categorization and voice categorization too, there's a whole set of studies we've done in parallel, is very reflexive optimal. So rules are helpful early in learning, but you've got to give it up fast and then move to a more procedural learning, and that really helps you get to better accuracies. We have computational models based on these brain regions that support this idea. But we've done a lot of studies where we looked at sources of individual differences, things like working memory, musicianship, aging, whether you're depressed or not, genetics. So these are factors related to that individual state or trait-based factors. We also did a lot of work subtly changing the training paradigm itself, right? So here's where we change the variability, the information content and feedback, the timing, put people under pressure, give better instructions, and neuromodulation. So we've done a whole bunch of studies modifying these. And I'm just going to walk you really quickly through several of these. So older adults are really bad at this task, and that's because they get stuck with a very poor rule and don't move on to better rules or more procedural learning. Musicians are excellent, so they use great rules initially in learning, and then they switch to a more procedural, reflexive, optimal learning. So they're very good at this task. And some of the examples of variability related to training, we can get better learning if participants are doing mixed talkers relative to block talkers, and that's because mixed talkers allows them to not kind of get caught up with bad rules that are talker dependent. Minimum feedback is much better than full feedback. So when we just give them wrong versus wrong, that was category 4, learning is better. So less is more, and that's because less is what the reflexive system needs. It needs the reflective system to go offline and transfer control to the reflexive system. But the reflexive system needs immediacy in feedback. So 500 milliseconds delay is most optimal for learning in this system. So anything beyond that really messes up learning. So when we delay the feedback by 1 second, it's not very perceptible, by the way, but it is perceptible to the basal ganglia. Suddenly it can't map the sound to the reward accurately, and learning gets poorer. Instructions, really good instructions help, we basically told them prior participants have found that listening to the pitch direction is a useful cue, and it is a useful cue, and people take that and do very well, even though by the end of training they're more reflexive. Also, performance pressure. So here participants say there's another participant that is also trying to learn, and both of you have to get 70% above to get the reward. And so then they start the experiment and the screen flashes and it says, your friend has got 70%, now it's all on you. Performance pressure messes up the reflective system, allows faster control to the reflexive system. Okay, so that's a lot about Mandarin tones. In the last 10-15 minutes, I'm going to talk about a topic I know a lot less about, which is voice. Don't let my abstract fool you, that's just to get you in here. Right, so voice models, neural representation of voices, have been very much derived from faces. So there's been a lot of work in the visual domain, and that's been adapted to the auditory domain. And as an auditory scientist, I hate this, right? Vision is something that doesn't even work in the dark. It's a joke. So these models basically make a case that there is processing on ensembles of neurons that is very dedicated to processing specific information, is highly tuned to voices in a preferential way. These are all work that is derived from models in vision. In fact, it goes on to say that there is a prototype voice that you're trying to match. So what's happening in these regions that respond to vocal sounds but not non-vocal sounds? The strip called the temporal voice areas is that it's doing very fine-grained analysis of voice. in a very, very preferential way, and is using some form of a template matching to an average voice. And there's lots of beautiful data to provide support for this. And led to development of this model by Pascal Bellin and colleagues. You don't need to get into the weeds here, except that this is very hierarchical. So there are processing units, and one has to go to another, and there's first processing units processes vocal information with great precision, passes it along to regions related to emotion, the extended network related to language, emotion, etc. And so this is the hierarchical prototype model. A long time ago, when I started studying models and contrasted models to prototype models, there's a lot of work in linguistics on exemplar models. And this is one of those studies that we did where we looked at this one region called the left middle temporal gyrus. This region is known to process words preferentially. So when you repeat words, this brain region reduces its activity. Okay, that may be counterintuitive, but it's more sharp, so it's less bold, less fMRI signal. Right? So when you repeat the words repetitively, it drops. When you repeat pseudo words, this brain region is not interested. So it's well known to be a word processing, lexicosemantic information extracting region. When I changed the voice, so the same word repeated over and over again, suddenly the response suppression goes away, suggesting that this region, which is a core part of the language network, is so fine-tuned to voices, sometimes even more than the temporal voice processing area. And following this up with several beautiful work from other colleagues looking at the language familiarity effect. How many of you have heard of this, the language familiarity effect? Okay. So very simply put, you recognize talkers better in native language than non-native languages. Okay, that's the language familiarity effect. And I'll just give you a quick example here. These are 4 Mandarin talkers. If you don't know Mandarin,
我们都在学习电脑打字。我们都在学习电脑打字。
我们都在学习电脑打字。
我们都在学习电脑打字。
Okay, so if your task was to differentiate those 4 talkers, you would have a lot more trouble than differentiating English talkers.
The girl is fixing her dress.
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 Right? Okay, lots of empirical data, so even if that didn't work for you and you were very good, this is a different audience than most people who don't spend their time talking about voices. Parashone in 2011 showed the very strong behavioral results where listeners are way more accurate for native speakers than non-native speakers. So you can see that difference between English talkers and Chinese talkers here. But what was really interesting was those with developmental dyslexia that have a phonological issue did not show the language familiarity effect. And what they argued was that voices and language and voices is just intertwined in ways that cannot be separated, and it's probably how the brain is processing information. Now, we followed this work up with some really cool collaborations in Montreal. And this is a series of papers published 10 years ago where in Montreal they had access to international adoptees. So these are adoptees from China predominantly who were exposed to tones really early in life, so usually less than 2 years. And then they moved to Canada and since then have not undergone any language training in Mandarin, don't know Mandarin, so it's almost like a hidden trace. And what they found was that tone representation is much more robust in these international adoptees, even though they can't speak the language, reflecting that these early representations are not overwritten or not lost, and they're somehow maintained in the brain, right? And here you can see the left planum temporale is more active for processing tones, and the longer experience you had in Mandarin, the more robust the responses were. What about voice learning? So in collaboration with Denise Klein and Shari Brown, we did a study in Montreal and basically found that robust language familiarity effect, as in a big advantage for native Mandarin listeners listening to Mandarin, but neither the adoptees group nor French speakers found a behavioral advantage. But in the left middle temporal gyrus, we found the much more robust representation of voices for Mandarin listeners relative to French listeners, but the international adoptees are right between. Okay, I want to spend the last couple of minutes talking about pitch patterns that convey very complex prosodic information related to saliency, uncertainty, contrast, prominence. Lots of work in linguistics using approaches in phonology that argue that there are fundamental prosodic units, and these units can communicate very rich information related to word prominence and pragmatic information. This is not very well studied in the speech science literature because these are very, very hard to do. But we've done this work looking at naturalistic speech, and these are in patients with intracranial recordings. So this is work with Taylor Abel, who is a neurosurgeon very interested in voice and in how we discern familiar voices. And the reason we got into this was there was a recent paper that came out in Cell from Liberty Hamilton and Eddie Chan, basically showing that there are parallel pathways in speech. So the traditional assumption has been everything has to go, get analyzed at the Heschel's gyrus, the auditory cortex, and then passed on to other information. Remember the model I showed you before, the Berlin model? So it's very hierarchical. So there's gross acoustic processing and then more and more fine-grained processing. So what they found was that speech information was directly transmitted to the superior temporal gyrus from the thalamus, ignoring the Heschel's gyrus. In fact, they then analyzed participants who had the Heschel's gyrus removed, and they showed no deficits in speech processing, in speech perception, right? But we asked if that impairs their prosodic representation. So the study just came out. I don't want to get into the details here, but all I can just say here is that lots and lots of electrodes across the brain respond to sound, and that's what you see here. So lots of responsivity to sounds. Some of these electrodes that are more distributed, but a lot in the Heschel's gyrus, are very selectively responsive to the different prosodic categories, right? Don't get into the nomenclature here. It takes 6 months to understand it, as I found out. But what was really interesting was that there was much more category level information in the Heschel's gyrus. Remember the part of the brain that seems to do nothing for speech processing is actively processing prosodic information in a very categorical way. The superior temporal gyrus, which processes spoken language units, phonemic information, featural information, is much less effective in representing pitch and pitch trajectories. And all that's showing here is that when we add the label of pitch accents, that explains the neural variability a lot more than just when a bunch of acoustic measures were added. All right, now what's really cool is we did a parallel experiment where we had monkeys, so these are macaques in Tobias T-shirt's lab that's also listening to Alice in Wonderland, which is the audiobook. And we do the same experiment, but in this model we have very, very fine-grained information, including some units that capture single neuron information. What we found was that the neural ensembles in these monkeys capture the acoustics with great precision, just like the human model. In fact, very little difference. So the units both in the Heschel's gyrus as well as the SCG respond to these different categories based on their acoustics. But when we add the label, it explains no additional variance, right? Suggesting that there's abstract representation of these categories in the Heschel's gyrus. I'm going to conclude by closing with the same, what I talked about in the beginning, which is how do we learn to transform sensory information to discrete auditory categories. I've talked to you about lexical tones, voices, prosody. I think something to appreciate is that it doesn't really matter what that category is. There may be some processing units that are specifically related to some of this, but for the most part, how we learn information has remarkable similarities. And so there's stability in the face of variability. I've shown you distributed neural representations of categories. So they're not hierarchical, they're certainly very redundant. So you have representations in the echelons, you have representations in the SDG. And I view these as task-related representations. So these are representations that learners are immediately using to just get the job done, okay? And they're redundant, parallel, and again, with the frequency following responses, I showed you that top-down guidance really fine-tunes early sensory encoding, and that individual differences are at least partially maintained by domain general systems and the reflective and reflexive systems that I mentioned. And so subtle changes in how you train people can really make a big difference in their learning outcome. So this work really requires a team, so I really want to acknowledge folks both at University of Texas, Austin, Pittsburgh, as well as Northwestern University, who richly contributed, as well as my lab called the Sound Brain Lab. And then I really want to acknowledge the funders. Since March 2025, and we've not received funds from the National Institute of Health. So it's been frozen at Northwestern. Just wanted to mention that was prime driver for a lot of this work. So right now, Northwestern is supporting all the research that's going on in the labs, but obviously that can't be forever. And I mention this because I know a lot of you here have their science funding either canceled or frozen, and I'm there with you in spirit. And to this audience, I think this quote stood out to me, which is, "A single voice may crack in thunder, but may choirs rise where silence once stood." Thank you.